So I will go through the main interest, not necessarily in front of this audience, so we are interested into sustainability and high energy density. And we are all struggling mostly because of the same reasons. So the high charge over reduce ratio for these divalent cation, which makes Coulombic interaction much stronger and mobility in general much more difficult. So this includes, for instance, the quite challenging task of finding interfaces that do allow for divalent cation mobility, in stark contrast with lithium. So we do have quite a challenging task of finding stable interfaces. And so for magnesium, strategy has been to try to get as passivation free as possible since the first Grignard-Reagent based electrolyte, which evolves quite positively towards the now state-of-the-art fluorinated alkoxyborate. And unfortunately for calcium, at the time there was no Grignard equivalent, so this has been almost discarded for quite a long time. And calcium has the additional advantage and disadvantage in this case of this 500 millivolt difference in terms of standard redox potential compared to magnesium. So it's virtually impossible to find a fully stable electrolyte against calcium. So we do have to deal with some kind of kinetic limitations, so some kind of passivation layer formation to try to deal with stability in these cells. So this is the reason why in 2013 we tried to revisit a little bit together with Professor Palassine and Fanny Bardet at the time at Toyota Motor Europe, the calcium system. So we quickly end up with noticing that calcium mobility and ion mobility in general in these systems is an issue. So we have very limited ionic conductivity at a very limited salt concentration and very high viscosity rise when we increase these ionic salt concentration. So an easy trick, of course, to improve mobility and reduce viscosity is just to increase the temperature of the system. And with this, we managed to do a little bit of calcium plating. At the time, this was purposely done in carbonate-based electrolytes. So we have done this in a CPC-based electrolyte, which form a very stable passivation layer at the surface of this calcium metal anode and provide some nice electrochemical stability window, even at elevated temperature. So of course, since then, the community has moved forward, and we have now electrolytes that operate at room temperature. We do have, we were quite puzzled by the fact that most of these electrolytes are boron-based, so the anion is boron-based, so this picked up our interest, and we tried to figure out if there was some interest behind this. So with fewer, more recent exception, let's say, on the aluminum BHFIP, on the aluminum HFIP, sorry. So here, I just try to convey a little bit what we have as an overview of our work, trying to pinpoint the main limiting parameters for metal plating. So we do have the issue of cation complex mobility within the solution, the dissolution energy at the interface, that can be an issue, the migration of the divalent cations through the passivation layer, as we mentioned before, and of course the nucleation energy barrier at the metal, at the substrate interface. So looking at these different parameters, but starting with the cation solvation structure, so trying to understand what is actually present in solution in our electrolyte. One interesting tool to look at that is Raman spectroscopy. So here we can have an insight on the free solvent molecule being present, the coordinated solvent molecules, and the same for the anion, so in this case TFSI. So we can have bands associated with the free anion in solution and bands associated with the coordinated cation, anion. So looking at these and looking at the comparison between calcium, lithium, sodium, and magnesium system, we can come up with different conclusions. The first one is that The interactions, so cation solvent, cation anion interactions are following the polarizing power of the cation, so they are stronger for magnesium than for calcium and so on. The other one is that we do have more solvent molecules present in the cation solvation shell for divalent cations. So we have between 6 to 8 solvent molecules for calcium and magnesium compared to 3 to 4 in terms of lithium and sodium. So we have much more bulkier cation complex to move around in the electrolyte. And potentially stronger interactions, so stronger, higher dissolution energy to be expected. So we can try to be a bit more quantitative with this Raman spectroscopy. And here we can also explore different solvents. So we can then extract the solvation number in terms of solvent with respect to the salt concentration in solution. Or the solvation number in terms of anions, so the presence of anion into the primary solvation shell of the cation present. And as expected, these solvation number of ion pairs is increasing while we increase the salt concentration. And as we use higher donor number solvent, we tend to be more resistant to the formation of contact ion pair in solution. And if we compare now for all other parameters being kept constant, calcium and magnesium, we do expect much more tendency to form ion pairs in magnesium-based system than in calcium-based system, as expected from the polarizing power of the cations. So now that we have a better glimpse of what we have in solution, we can move to the passivation layer. And one of the main difference that we noticed right from the beginning in this system was the difference in electrochemistry in calcium BF4 based system or calcium TFSI based system. In calcium TFSI it's very nice, super flat, so no redox feature at all. While as I was mentioning, then we do have some degree of reversibility with calcium BF4. So we obviously try to understood the main difference between those two systems. So here, one of the things that we first started with was to analyze the interface in this system, in these different electrolyte formulations. So here is a bit of a trick that we used to not to have to deal with sample preparations to measure SCI thickness for TM measurements. So we used metallic particles, not nanoparticles, but particles, that we can basically polarize, form the passivation layer on top of it, and then pick it up and put it on the TM grid without extensive sample preparation, let's say. So of course we still have to go through ultra high vacuum for TM. So this is to be determined if this is the real SCI we got in solution, but at least this gives us a first hint on the difference in the different systems. So we can see that for calcium TFSI based electrolyte, we do have much thinner passivation layer being formed. In both cases it's fully conformal, so we have passivation layer everywhere covering the full particles. But then this seems to be fully blocking actually. So from XPS measurements, what we can then take out is that the decomposition product in TFSI-based electrolyte are mostly carbonate-based. So those comes from the solvent decomposition. And in the case of BF4-based electrolyte, we mostly have, sorry, that's the other way around. No, we mostly have anion decomposition products. So we have calcium fluoride, of course, but also some borate being present, which is basically the main different species that we have in these two systems. So we don't know much about these borate species yet. What we know is that we have a full substitution of the BF bond. So we have BO3 moieties. So we fully substituted the salt ligands. We do expect that we have this kind of nucleophilic substitution in solution. So we do have replacement of the fluor with the ringed open molecules from EC with concomitant formation of calcium fluoride, but I will come back to the potential mechanism later on in the presentation. So what we wanted to observe, of course, was is this borate-based decomposition product one of the key for calcium plating and stripping. So to ascertain that, we actually polarize a stainless steel substrate in calcium BF4-based electrolytes, forming this passivation layer, borate-containing passivation layer, and then we transfer these passivated substrates to the same electrolyte as previously, so TFSI-based or BF4-based. And then now not only do we start to see some redox feature for TFSI-based electrolyte, but we do also see an improvement in terms of kinetics for plating and stripping with TFSI. So in conclusion, the borate-based containing passivation layer is enabling calcium plating and stripping, but the nature of the electrolyte is actually also playing a key role into the plating stripping kinetics. So one way to rationalize that is to look at the Raman spectroscopy again and the solvation structure of the cation in solution. And what we can see is that for TFSI-based electrolytes, at these 0.5 molar concentration, we actually do not have contact ion pair in solution, basically. While in case of calcium BF4, we do have quite significant amount of contact ion pair in solution. If we consider now the binding energy of these complexes, we can expect actually much calculated from DFT, so we can expect much higher dissolution energy for contact ion pair complex in solution than for a fully solvent-solvated cation complex. So we do have to spend more energy towards dissolution in the case we have contact ion pair formation in solution. And with respect to these calculations, we can also expect for similar species in solution, higher dissolution energy to be required for magnesium-based system compared to calcium-based system. So now, of course, working with calcium BF4 is actually not trivial. Most of the salts that are commercially available are really wet. So most of the time you buy them and you receive them almost as a gel. So it's quite tricky, very tricky to dry. Most of the drying procedure involve hydrolysis. So you basically decompose the salt. And if you check on the real salt concentration in solution with NMR, for instance, you end up with a very low salt concentration, really, in the solution. So you never know what you are working with if you don't pay attention to that. We tried the synthesis of the calcium BF4. It's feasible, of course, not that easy. We can end up with much drier salt, but still it's quite challenging. So we try to explore a different approach as well, to use boron-based additives. So for instance, this BF3 diethyl ether was used in calcium TFSI-based electrolytes. So this was a way to bring the boron in without using this BF4-based electrolyte, let's say, still in ECPC-based electrolyte. So here you can see that the electrochemistry is relatively similar. So we get basically the similar, slightly improved electrochemistry than with the calcium BF4 in this case. And if we now have a look at the passivation layer, we can see that the passivation layer in this additive-based solution is very reminiscent of the one that we obtain in pure calcium TFSI. So it's, well, once again, very conformal, slightly thicker, and very homogeneous throughout the surface of the area, the substrate. The XPS tells us that we have similar species than with the calcium BF4-based electrolyte, so we still go back to this borate-based containing passivation layer. And we do have actually a higher extent, a higher content of these borate species in the passivation layer when compared to the calcium BF4, and lower amount of calcium fluoride. So one of our hypotheses was that we were forming this adduct in solution, so we were complexing the EC with the BF3. So to try to ascertain that was, we went to Matic Lozinček in Ljubljana as well, to synthesize it directly and use this as a co-solvent. And indeed, we were basically obtaining the same electrochemistry and similar passivation layer being formed using these as a co-solvent than when using the BF3 diethyl ether as an additive. So here the main mechanism that was proposed by DFT calculation was the fact that these complexations actually favor the ring opening of EC, which then tends to polymerize through successive nucleophilic substitution of these BF bonds. So this is one of the idea we have on the formation of these species, but of course we still need to understand what is this kind of polymer, to which extent do they grow, and how is their full coverage of the passivation layer. So with this knowledge now on the potential role of borates in the passivation layer, we came back to have a little look at the literature, what has been done in the field. So different system here, the calcium BH4 was expecting to work forming a calcium hydride at the interface, continuously growing in this case apparently. This has been challenged recently, mentioning that actually the calcium hydride was included into the calcium metal during plating with a real surface film that was actually a combination of calcium carbonate, borate, and oxides. So of course we were very tempted to say that, okay, this is once again one of the examples that borate is actually playing an interesting role here. However, I wouldn't, as counterintuitive as it might sound, fully discard the role of calcium oxide here. When we calculate the migration energy barrier of calcium into different compound, we can see that we have a 1 electron volt migration energy barrier, which might sound prohibitive for migration. In this case, however, we have always to keep in mind that usually the 700 millielectron volt energy barrier that we thought as a prohibitive barrier is always thought for cathode material, for cycling, so micrometric size particles. But if we think about a nanometric scale layer, then we cannot exclude that actually calcium oxide is at least partially allowing some degree of mobility through it. So then the question, of course, is what is the status now for the state-of-the-art electrolyte, so the BHFIP-based electrolyte. So this is still a work in progress together with Jan Biteng from Slovenia, but and I hope we'll be discussing it soon. But I can already tell that, well, we do see passivation layer, and we do see borates at the interfaces. So now, moving to magnesium interfaces. So here we started up with a very basic system based on magnesium TFSI with glymes. So here you can see some very characteristic huge voltage hysteresis for plating and stripping using this electrolyte. And we were interested to see, so one of the main culprit, of course, that we can pinpoint is the decomposition of the TFSI anions. So to try to minimize this impact on the passivation layer resistance, we went for lower salt concentration, and we can actually start to have slightly better reversibility. So we don't have this 2 volt voltage hysteresis now by lowering the salt concentration. Still, of course, the electrochemical behavior is not optimal, but that's a nice playground to see the basic trends basically in this system. So from XPS measurement, we can definitely see that the passivation layer is relatively thick. We do not see the substrate here, the titanium substrate. There is no significant difference into the basic composition of this passivation layer. We have the same species, depending on the salt concentration. However, what we can notice is the difference in stoichiometry of these species. So for lower salt concentration, we do have richer organic passivation layers that are richer in organic components. And at higher salt concentration, we do have more anion decomposition products. So basically, by decreasing the ion pair formation in solution, we tune a little bit the passivation layer formation in this case. Sorry, so I forgot to mention that in all cases, even if we take care of drying the electrolyte, we always get to see the magnesium oxide, of course, to similar extent, actually, regardless of the salt concentration. So we do have, of course, traces of remaining water in solution. And to try to get rid of that, we also play with the presence of butyl magnesium, so not containing chloride in this case. So this is dibutyl magnesium diethyl iterate in this case. So in this case, of course, the presence of these additives was significantly improving the overall kinetics of plating and stripping. We get decent cycling upon time. So if we look at the interface now again, so what we can see is that actually we have much thinner passivation layer in this case. We can see now the substrate basically. We do have much less decomposition of the anion, so much less magnesium fluoride in solution, much less magnesium oxide as well. So we do get the water scavenging properties working here. We have less oxides, and we have these additives that is, I would say surprisingly, limiting the anion decomposition as well. So one of the potential explanation for that is actually the fact that if we look at Raman spectroscopy, it does seem that the butyl magnesium is actually playing a role into the TFSI coordination. So we do have some degree of complexation of the anion in solution due to the dibutyl magnesium, which is supported by DFT calculations, as we can actually form some stable complexes with TFSI, with dibutyl magnesium in these cases. So we do think that here that's one of the interesting approach, I would say, for divalent cation in general, is to try to somehow immobilize the anion in solution and to make it less available for decomposition at the interface, and also reduce its mobility, which is always beneficial for divalent cation-based system. So one of the other parameters that we explored was the impact of the substrate used for metal deposition. So here you can see a deposit on titanium versus stainless steel, all other parameters being kept constant. We did observe improved overall kinetics for plating, for magnesium plating, when using titanium instead of stainless steel or other conventional substrate. One of the potential rationale behind this is the fact that magnesium and titanium are actually very alike, crystalline structure-wise. So they do both crystallize in hexagonal close-packed structure, by contrast with copper, aluminum, nickel, and stainless steel, and so on, that are cubic. We also have relatively low lattice mismatch, actually, between magnesium and titanium. So this sounds like, well, an interesting approach, at least to us, to try to also improve the overall nucleation of the metal by playing on the crystalline similarities with the substrate. So now, moving on to the cathodes, if I have a few minutes more, yeah. So one of the cathode we have been exploring together with Rebecca Marcia and David Messereyes was the organic cathode, so here the polyimide, that are, well, I would say a relief for us to be able to test something that cycle for divalent cation-based system. We have been passing years struggling with something that have only one charge or one discharge, or that was a bit depressing, I would say. But now we have these organic-based material that do cycle I would say very well. I was actually surprised at the beginning to see the rate capability for this system. So same goes for magnesium. So here you can see cycling. We went up to 1C, but we can definitely go higher, and 2C is not much lower. So the cyclability is actually quite good. We confirmed from infrared operando that we do have the same basic mechanism, so the annulation mechanism. So we coordinate the carbonyl here with calcium or magnesium. And one aspect that I would like to emphasize here is the strong impact again on the cation solvation structure in solution. On the cyclability of these cathodes in this case. So as we change the salt concentration, here in this case we are dealing with magnesium-based electrolyte. As we increase the salt concentration, we start to observe a very strong cycle capacity loss upon cycling. And this is actually being alleviated by the use of lower salt concentration in solution. So we do suspect that here the formation of contact ion pair is also highly detrimental to cyclability. And we can see here from these SEM images that when compared to the pristine material, so we can have, after cycling, we can have much better retention of this overall morphology in the case of the very low salt concentration in solution, and we start to form very thick and most likely highly resistive passivation layer in the case of high salt concentration in solution. So here this is just one additional example that cation solvation structure is very critical, I would say, not only on the anode side but also on the cathode side to maintain stable interfaces. So with this, I come to the conclusion. So I hope that I convince you that engineering, or at least understanding the cation solvation structure, is definitely a key things we need to do. I would say in particular for divalent cation system, even more than for lithium and sodium, which are usually highly dissociated, because these can play a role definitely in the passivation layer formation, the cation mobility in solution, and impact the dissolution energy barrier we have to pay for removing the cation solvation structure before entering the passivation layer. So this is true for calcium, and I would say even more important for magnesium, because we do have this stronger tendency to form contact ion pair with magnesium. So this is, as I was mentioning, very important for the anode side, but this is, I guess, also very important on the cathode side. So usually we should expect contact ion pair to be more stable towards oxidation. Even though, in this case, we do observe more decomposition product in the presence of contact ion pair. And we do believe that this is just because of the fact that we are bringing the anion really next to the redox center and favoring, if any possibility, the anion decomposition, actually. So with this also, I would like to remind that, we are still struggling to understand the lithium SEI. So, we have a long way to go, but hopefully we are going in the right directions to better understand this system. At least to understand the trends that we need to follow to improve it. So with this, this is most likely the most important slide. So I would like to thank, of course, my team at ICMAB in Barcelona, people from Chalmers for Raman spectroscopy measurement, at Aurbach synchrotron at the Miras beamline for infrared spectroscopy and operando test, Karine Davoine at LRCS for TM measurements, Rémi Detriver and Moat Radi from Po for XPS measurement, Piotr for DFT measurement, Matic from Ljubljana for crazy synthesis using BF3, and of course the fundings, and you for your attention. Thank you for your attention.